Record up. All right, you're on.
Oh goodness. I'm here to promote my job SI, and I'm pulling up my little flyer that I made, uh, which I can't find. Oh, right here. Sorry. I'm here to promote my job SI. Um, I kind of just want to give my personal experience so far. I started this semester, and I plan on continuing in the future. This is some information about the jobs that are offered through the Student Learning Access Center, Academic Center. And I can personally speak on being an SI leader. Like I said, I started this semester. I'm SIing for organic chemistry. And out of all the classes I've taken at Texas State, I feel the most confident in organic chemistry. Now, that is one, because I really enjoy it, and two, because I'm now taking it for a second time with a different professor, and I'm learning so many things that it kind of went over my head the first time around. I'm gonna be taking the MCAT next spring. Uh, Looking forward to it. And I gotta say, I feel very confident when it comes to taking the MCAT in regards to how I feel about chemistry. And uh, you can also SI for general chemistry courses, I'm sure y'all are aware of, and up to OChem 2 for now. There are also opportunities to SI for other subjects that are not in chemistry, but I figured since we are in a chemistry class right now, that would be relevant. Um, the other positions that are offered by Slack are the Slack Lab Tutor. Traditionally, they would be on the fourth floor of the Alkek library, but I think they're providing online services right now. So if you don't want to have such a, uh, if you don't want to do the approach of an SI leader where you're kind of leading a group of people and helping them out in a collaborative way, one-on-one tutoring might be the best thing for you. I also have a lot of experience in tutoring, not with Slack, but through other areas, and the same thing applies. This constant reinforcement of material that you've learned in the past is super beneficial. I'm taking biochem right now, and Gen Chem's coming back, and it's crazy. So having that reinforcement is very, very good as you continue to move forward in your undergraduate careers. So the last one that I want to talk about briefly is VASC. This is the veteran. This is kind of a tutoring service for veterans. I think the acronym is like the Veteran Academic Success Center, and this is a service if you are a veteran, which I don't know if anybody is, but if you are, this is available to you. It's another tutoring service provided through Slack. But yeah, the information is right here. This is a crude summary of everything that is offered. The deadline to apply is October 26th. And you can apply by visiting www.texasstate.edu/slack. If you have any questions as well, you can always email me. But yeah, that's all I gotta really say. Uh, Definitely try it if you're interested.
Uh, okay, and Nick, can you post that under flyers in our?
Yeah, yeah, sure.
You can go find this on flyers if you want more information later. Okay. Okay, so due this week, of course, we have mock exams. Sorry, got a little flustered on one of them. So I have a mock exam set today from 10 a.m. to 6 p.m. and a mock exam set tomorrow from 8 a.m. to 6 p.m. If you had trouble the first or second time doing this, go ahead and take another one just to make sure everything's working now. If everything worked the first time and you just want to double check, make sure everything works the second time, go ahead. Those are available to you. Again, it's just 5 questions. It's not graded. It doesn't matter. All I want to do is make you comfortable with the testing platform. Okay. So those are available for you. And so there's today and tomorrow. And I will not have any mock exams on Friday. We take the exam during class time on Friday. Do not come to the Zoom meeting. Just log into Top Hat, sign in with Proctorio, and take your exam. You'll have the normal class hour to take it unless you have some other accommodation. And then at the end of it, you can be kicked out once and I can let you back in. I'll monitor live. And then at the end of the exam, you go ahead and submit or close it out, and then that saves all of your results. So I believe there's a save button at the end of each question. You can review as much as you want and change those questions until you log out, and then those are your locked answers, okay? There should also be a table of, periodic table of content, I'm sorry, periodic table of elements at the top and bottom of the exam so you can scroll through and use that for reference, okay? So the only thing you'll need for the exam is your computer, a photo ID, and some scratch paper and a pencil. No calculators, no books, no notes, no nothing, okay? Yes, the test is due at the end of the class period.
Will the test also be 5 questions?
No, the test is going to be 30 questions, multiple choice. And they are going to be similar to what we saw in homework. They're going to be the same kind of style of question. Most of them are going to be multiple choice. As long as it's a picture ID and you put it in front of the computer and it'll match your face to that. I had one person who actually had glasses on their ID and didn't wear the glasses, and it wouldn't. So whatever's on your ID, go ahead and wear glasses or don't wear glasses depending on how your ID is. So either one will take it as long as it's a picture ID. It's got a pretty cool AI program that sifts through those are. Okay, so so whatever your ID shows, wear whatever that is. So obviously no hats, and so don't wear any dark sunglasses, don't wear hoodies. The computer will kind of freak out about that. So we're not playing poker, so just go ahead and wear what you would normally wear and try to match your ID as much as you can, okay? All right, let's see. Homework is due midnight tonight, and that's because as soon as it's midnight, you can use that to review. It'll tell you what the right answers are, and you can use that as a study tool. Okay, any questions about administration before we finish up Module 4? Okay, I'm going to start drawing up Module 4 while you're coming up with an answer here. And so what we're going to do is we're going to finish out Module 4 with the last little sections here. And let me go ahead and share my screen.
I'm sorry, I have one quick question. So you said we have the like class hour. Is it an hour or 50 minutes?
I'll give you the whole hour. It'll
okay.
Open at 10 a.m. It will close at 11 a.m.
Okay, thank you.
If you show up a couple minutes late, you still have the full time to take it. Okay. So
sorry, I have one more question. So like since we have 10 through 11, can we like start the whole exam process like at 9:55, or do we have to start at 10?
You have to start at 10.
Okay,
The exam will open at 10 and then give you that whole hour. The reason we do this is what we call test security. So we don't want you to rush through it and finish early and then start posting stuff. And it actually takes pictures of you if you're trying to take pictures of the screen, and that pops up as an aberrant behavior and you're flagged. So don't have your phone out because it will see your phone, and because your phone actually emits an IR beam to it, it'll pick it up and it flags you right away. So, so we start, because of test security, we start exactly at 10. You can start anytime after that, but it does close at exactly 11. So you need to be in that kind of window, okay?
Okay, thank you.
All right, so where we ended up last time was talking about cyclohexanes and the fact that if you have just room temperature is enough energy to get it to go through all these different conformations, and any one of these conformations, the amount of the solution that is in these conformations is directly related to that energy of transition here. So the more stable, the less potential energy it has, that's going to be more commonly found in the solution. The higher potential energy is, the fewer of those molecules are going to be found in that configuration. So what we also learned was that they have names for the different positions. And so the carbons themselves are in the ring, but the substituents can either be in the axial position, which are those that are in like all aligned in an axis up and down through the middle of that ring. And then the other ones are kind of staggered around the outside as equatorial positions, okay? So we need to keep pay attention to the axial and equatorial positions, okay? In addition to that, we learned that, whoa, don't go anywhere, that we also had a boat conformation, and it had one new name called flagpole. And flagpole are the two hydrogens that are going to be, or the two substituents that are going to be butting up against each other. Okay, so this is not as stable as the chair, but it is possible at room temperature to see this configuration. Okay, so now I want to show you an easy way to draw the chair configuration. Okay, so I know it's kind of hard when you first look at it, but when we start doing this, it's easiest to draw it in this way. We start with just two parallel lines like this. Oops, where are you? There you go. Two parallel lines. All right. Bring it up. Change the. Aren't you writing? All right, now let me close out and open it again. I don't know why it's not writing. There we go. Okay, there we go. So the easiest way to draw this cyclohexane ring is to go ahead and draw two parallel lines diagonally, and then draw one bird's peak on one side, one bird's peak on the other side, and then you start filling in where the hydrogens are. And if the peaks are going up, you're going to first put a hydrogen in the axial position right here. And then if the peaks are going down, you're going to put the substituents in this axial position at those points. And then know that all the other positions, because there's at least one other position on there, are going to give us those equatorial positions. So the idea is you look for the up peaks, gives you your axials. The down peaks give you your other axials, and everything else is going to be those equatorial positions, okay? So this is a pretty easy way to remember how to write it. When you first start doing it, you're gonna kind of draw it all wonky, but with just 5 minutes of practice, you'll be able to draw it just right. Okay. So now that we can draw these things, when we take this ring and we start with, let's draw attention to this carbon atom here. Okay, that carbon atom there is up. It's on a peak pointing up right now. And when it flips, both of the two ends are going to flip positions such that this carbon is now going to be pointing down, okay? And it'll flip back and forth, okay? When it flips, your things that are axial become equatorial, and your things that were equatorial become axial, okay? So the ring doesn't break, nothing moves. All that happens is as you flip from one position to the other, your axials turn into equatorials and your equatorials turn into axials. So what this means is if you have a big group attached somewhere on your ring, it's going to have a preferred conformation because of sterics, okay? And so what we'll do is we might draw the ring one way and look at, oh, this is a very big substituent. It doesn't want to be in that position because of sterics, and we have to flip that ring to put it in that other lower energy conformation. So what do I mean by lower energy conformation? Let's start looking at the different kind of conformations possible. So let's start just by replacing one hydrogen with a methyl group. Methyl group's not that big, but it's about 4 times bigger than a hydrogen. So it plays a role here, okay? So if we drew it out flat, what we'd see is something like this, right here. And remember, our solid wedge there is coming out at us. So when we first draw this, if we take our little thing and we're gonna put that one down and this one up, and when we first draw our cyclohexane on the side right here, we're gonna draw it looking like this, okay? Now, in that drawing, because that methyl is up, and that methyl is up here, okay, we're gonna draw it in that axial position. However, that axial position has it closer to these hydrogens here than if it was in the equatorial position and these hydrogens here. They are much closer, and therefore by sterics, it's going to force that methyl group to try to be in the equatorial position. Remember, it can flip back and forth as long as it has heat. So it flips back and forth, and it tries to maintain having that large bulky group in the equatorial position. But it's not 100%. Because you have heat, it can flip back and forth, but it prefers to stay at that position, in this case, 95% of the time. As that group gets bigger, that percentage of time is going to be higher and higher and higher. Another weird way to look at it is this configuration right here. And so if we held our ring completely flat, you would see that that was all there. And again, our ring never looks like this in real space because it doesn't want to be flat like this because all the bonds are all at the wrong angles. Okay. So, but the idea here, now this drawing here actually shows how big this methyl group is compared to the hydrogens that were there before. And so this big methyl group here wants to be way out here instead of butting up against those two axial hydrogens. So basically what we're saying is any large group prefers to be in that equatorial position and it just has to undergo a ring flip to do so. Okay. So in this particular case here, we can explain it using that Gauss and the Gauss and eclipsed format to tell us why this might be. And so in the case of if we redraw our methyl group that is in that axial position using the Newman projection down this bond here and this bond here, what we see is, I'm going to change colors here, is the methyl group is now in the Gauss position to that other carbon on the carbon in the front of our, the number 3 carbon. So we have in our condition, like remember when we had just propane, and when we had those two methyl groups closest together, but not eclipsed, that's called Gauss, okay? And that's higher in energy than when they are completely opposite each other. When they're completely opposite each other, that's called anti. Now, if we were to then flip our ring from having it being axial to being in this equatorial position and translate that into our Newman projection, what we see is our methyl group right here is now anti to the next closest carbon, okay? It's not Gauss because that would be here, it's anti to this one, meaning it's of lower energy because of sterics, okay? So not only can you imagine it as the big bulky group wants to be around the periphery of the cyclohexane, but looking at that Newman projection, you have another way to validate that that methyl group would prefer to be in an axial position. And it turns out to be more stable by about 7 kilojoules per mole, okay? Now, that's not very much, that's like 10 degrees of heat. So 10 degrees of heat, you can get it flipping back and forth. Okay, so that was just for methyl group, okay? So as your groups get bigger and bigger and bigger and have bigger electron clouds, the percent of the time it's going to be equatorial is going to get higher and higher. So chlorine, okay, it has 3 lone pairs on it. So those lone pairs are the part that's taking up space. And it's equatorial about 83% of the time. With just a methyl group there, we're looking at that 95% of the time. Just going from a methyl group to an ethyl group, because it's not branched and that methyl group can be further away from the ring, it doesn't change it very much. But now, once we branch it, that other methyl group is starting to take up a little bit of space closer to the ring, and it goes up. And by the time we get to this T-butyl group, okay, it's 3 methyls off there, that means 99.9% of the time, it's going to be in that equatorial position. And it all has to do with sterics. Okay, so what if you have 2 things on the ring, okay? So if you have 2 things on the ring, the best thing to do is, if they're in a correct position, try to get them both at the equatorial position. So let's see if we can do that with this particular isomer here. Okay, switching back to red here. So in this particular case, we have this 1,2-dipromo. And notice that one of the bromines is coming up out of the page and one of them is going into the page. So that gives us our trans configuration. Remember, we have that trans in cyclohexanes because it's fixed. It can't free rotate. So if we redraw that to give us our flat plane kind of showing where our axials and our equatorials are, we'll actually end up with one configuration is going to be like this, because our bromine was up here. We have our bromine up in an axial position. Our bromine was down. We have our bromine down in our axial position. And that puts the hydrogens that are on those same carbons in an equatorial position. However, Steric says that those bromines, which those big electron clouds, don't want to be in that position and will ring flip to try to get them into the equatorial position. And it turns out, if we do that, the axial becomes an equatorial, and this axial becomes an equatorial here. And so we can actually get both bromines in an equatorial position, and that means that it's going to be in that, with both bromines in that equatorial position most of the time, probably more than 95% of the time, because we have two big groups, okay? So what if you have a competition between sizes? Or what if we had the other isomer, okay? Can we do that same thing and get them both equatorial? Now, the problem is no, we can't, because in this case here, we had an equatorial, we had a bromine facing up, solid. So the bromine's facing up, so we're gonna draw that in the axial position. This one was facing down, and it turned in the last example, and it was able to get in the lower axial position. But because it's facing up, we have to have a hydrogen in that down position, that axial position, and that places the bromine in an equatorial position. Okay. So now we have one axial and one equatorial, and if we ring flip, the axial becomes equatorial and the equatorial becomes axial, but guess what? We still have one big group in that axial position, okay? Which means either one of these configurations are going to be about the same in energy, so you're going to have about 50-50% one versus the other, okay? So if you can get them both, you should get them both equatorial. If you can't, it's going to be a 50-50 mixture of the two. Now that's if they're the same size. So if they're different sizes, then you have to worry about where can we put them. Okay. So let's try this with a tri-substituted cyclohexane. And in our first initial drawing, we have this methyl group up, this methyl group down. So when we draw this, this is our first time, this is going to be an axial position, this is going to be an axial position, and this is up, so this is going to be an axial position. Okay. So let's draw that first one with those in axial positions. And so this methyl group is going to end up being this methyl group. This methyl group is going to be axial, but on the bottom because it's pointing down. And this last one is going to be the axial group on the top, pointing up, because these two were pointing up. This one was pointing down. Two axials, one axial. Okay. What's the probability of having three large groups being in the axial position? Pretty low, right? Because they're sterically hindered. So when we flip this, we have to flip the ring. And so this end that comes up, this end goes down, and everything that's axial is now equatorial. Okay. So when we get the groups so that all three methyl groups are equatorial, that's going to be the most stable conformation of the system. Okay. So in these cyclohexanes, once you have one substituent on them, you're going to have a preferred orientation. It's going to be preferred, but not 100%, just preferred. When you start getting bigger and bulkier groups, it's starting to shift more and more toward that more stable conformation. Okay, and that is that. Now, I'm going to ask one question, and then we're going to head off to the review. So, what if you had a methyl group and a T-butyl group on the same ring? and you could only put one of them in an equatorial position. Which one would be in that equatorial position? So you should start thinking, well, the methyl group's this big and the T-butyl group is much bigger. So the T-butyl group is going to be the one that is going to be on the equatorial position. Even if the methyl group's axial, it's still going to prefer that because the largest group is always going to try to be on the equatorial position. Okay, great, great. All right, so let me move on to, any questions on chapter 4? So these orientations of cyclohexane tells us a lot about energy, and that those bonds, those sigma bonds, have a lot of mobility. When they're not tied in a ring, they can free rotate. When they are tied in a ring, we still have some flexibility. And it's all about trying to get to that 109.5 degrees, if at all possible. Okay, so I'm going to go to the review. Now, I emailed these slides. These slides are also on Canvas here. These are the top topics, the hot topics of these different chapters here. And so understanding this general idea and knowing how it kind of fits together with the following one is what we're looking for in our review, trying to be able to know what they are and know how to use them. Okay, so the first thing is that, of course, we're going to fill our orbitals from the bottom up. And then once we fill our orbitals from the bottom up, we look at our valence electrons, and our valence electrons tell us how many times it's going to bond, right? If we have 6 valence electrons, it's only going to bond twice because it only needs 8 electrons. If we have 4 valence electrons, it's going to bind 4 times to get those 8 octet electrons, okay? So, and we can find where these are just by using the periodic table. We want to use the periodic table for everything. Try not to memorize very much. Try to look for trends on your periodic table. Remember, electronegativity trends on the periodic table. Size trends on the periodic table. So know how those different trends work within the table. And again, there's a table posted at the beginning and end of the exam. Okay? Know this trend on electronegativity, that because that electronegativity leads to bond polarity, leads to bond strength, leads to where they show up in the IR. Oh, I forgot to put that table. I'm going to also send out a table on most important things for IR. So again, that difference in electronegativity leads to bond polarity. And bond polarity leads to a couple different things. The types of bonding you can do, dipole-dipole, ion, etc. Or whether it's nonpolar, has a nonpolar bond and only can do van der Waals forces. So see how electronegativity ties into bond polarity, ties into the type of bonds we make, covalent versus ionic, and ties into the strength of those bonds. I will not give a chart on electronegativity. You must be able to follow the trend on the periodic table. Okay. Know your Lewis structures, and know that a valid Lewis structure has to have the right number of electrons, or it must have formal charge. Okay, for example, the carbocation, this is a valid structure for a Lewis dot structure for a carbocation because it has charge. Okay, these are valid for neutral because they show where the lone pairs are, and these are valid for anions because you're showing charge. Remember your Lewis dot structures, it really helps a lot in identifying polarity and reactivity. Okay. The other thing it tells us is bond hybridization. Okay. It's very important to know your bond hybridization. sp3 and is tetrahedral. sp2 is trigonal planar with a lone p to do other bonding. And that lone p does a pi bond with another p orbital. So, and then an sp is 2 similar bonds and has 2 p orbitals that can pi bond with other p orbitals. So keep in mind your hybridization and the shape of those hybrid orbitals. Okay, and that shape of the hybrid orbital lets you learn the molecular shape. Molecular shape takes into account lone pairs as well as hybridization. Okay, so we need to look at our hybridization plus whether or not we have lone pairs. That's going to give us our molecular shape. Okay, know the 5 types of intermolecular forces. Okay, so ion-ion, we probably won't use a lot of that in here, but the ion dipole, we might. Hydrogen bonding is really big in things like carboxylic acids, alcohols, and amines. Dipole-dipole interactions are other polar bonds like carbonyls and things that don't have charge. I do suggest you review the homework questions for the test. They're going to be written in the same style, so especially for style. And then the induced dipole is our weakest force, and only the hydrocarbons have this force because there are no other forces available to them. So the relative idea here is that our London forces are weakest, our dipole is higher, hydrogen bonding is higher, ion dipole, and ion-ion is our strongest. So just that relative trend, you don't need to know the numbers, you just need to know that there's a trend with those things. And you need to know how these different types of interactions affect boiling point and melting. Stronger the force, the higher the boiling point or melting point. Okay. Also, remember your resonance structures, okay? Resonance structures are equivalent. There's no reason why we can't have this negative charge be on this oxygen. So when it moves around, you need to figure out that they're equivalent structures, and that sometimes when you calculate out your formal charge, you'll see that you're spreading charge out over multiple atoms. And so that's kind of one of the driving forces for resonance structures. Okay, so that's chapter 1. Any particular questions about what we need for chapter 1 here? It's all about the nature of our sigma and pi bonds, okay? Knowing how to make them, knowing where to find them, and knowing what shapes they are. Okay, all right, so then we moved on to chapter 2, and the whole idea of these functional groups and how to name them and their priority, okay? So we had a lot of practice in our group activity, which I'm still grading, and so did I post the key to that yet? Interesting question. Yes, I will, after the exam is done, I will, I have a target average and for the exam, and I will try to, if need be, curve to that average. I've gotten really good about not needing to curve it or curving it by a couple points, but I have a target class average that I try to maintain, and I'm getting closer to it, but if it's not there, I will, yes, curve up to that class average. Okay, knowing the priority of some of your major groups like alcohols and ketones and carboxylic acids, those are going to be very important. So you're probably going to have to name a couple things. You know, we have about, let's see, we have 30 questions. No, it's 25 questions, sorry, because of the time. And so you're going to have a couple nomenclature questions. So you want to be able to name these things and know these different functional groups and their priority. Beyond that, you want to follow all your basic rules. There's a rule, there's a pattern for everything. Start with the longest, identifying the priority group. Find the longest chain, identify everything, number everything, put everything in, you know, identical substituents can be di, tri, tetra, follow all those specific rules. And then when you get to alkenes, don't forget you have an EZ rule or a cis-trans rule. So make sure you understand how to do priority. The priority is almost always based on atomic number, but if you have things that are the same atomic number, you have to go to the next atoms out, okay? So this is taken out of that nomenclature review that is on Canvas, and so you can download that and work with that to help you study. Okay?
I have a quick question.
Yes.
On the exam, is it all 30 questions are multiple choice? Are there going to be questions where you have to like type in the nomenclature?
No, it's all going to be multiple choice for the exam. And that's why I have you do the group project so you get practice writing and drawing.
Okay, thank you.
Because it's the auto grading function's really finicky. And you put a comma in the wrong place, it counts it wrong, even though it's 99% right. So that's why I do that. Okay, again, this is your functional groups and how your name changes with the functional groups. Make sure that you know how to name these things as the functional group changes. And know your priorities for to do your naming complex things. Figure out your highest priority thing, and then everything else is substituents. There's no other priority after you identify that highest priority. Everything else just counts as substituent, and your substituents are always done in alphabetical order. Okay. Let's see, will we be given anything on functional or IR groups in the exam? Or do we, I'm gonna upload a figure for you of what I really want you to know. I want you to know which zones the different types of bonds are. So hydrogen, oxygen, hydrogen bonds show up where? Nitrogen, hydrogen bonds show up where? sp1, sp carbon hydrogen shows up where? Where does a carbon-carbon triple bond show up? Where does a carbon-nitrogen triple bond? Where do carbonyls show up? Those are the types of things I want you to know. I want you to know because in IR, we're looking at a specific bond, not necessarily a functional group. We're looking at those bonds. Okay, so it's going to be individual bond pairs. Does that answer your question? Okay. So if you know that each zone has certain types of bonds in it, then you are where you need to be for this class. And then when you take spectroscopy from me again, you'll get a much more in-depth. And again, knowing that the substituent is the thing that comes first, that's everything that's attached to it that's not the parent chain name. The prefix is the number of carbons in that longest chain. The infix is if you have alkanes, alkenes, or alkynes, those have to appear in your answer. And then the suffix tells you what the highest functional group was. Okay, so this process, it's embedded in there, but I wanted to draw attention to the idea that substituents come first, prefix is number of carbons, infix is whether or not you have single, double, or triple bonds, and suffix is the functional group that names the compound. Okay, and don't forget the acetyl group. This acetyl group is kind of a special name. It's so common in organic chemistry. Knowing that this CH3Cl carbonyl group here is the acetyl group is going to be important for not only this exam, but as we go forward, we're going to say, oh, we're going to add an acetate. And so knowing that that acetyl group is very common, and we use a lot of it. Okay. Okay, that takes us through nomenclature. I'm going to add one slide to the track site and email it out about IR, the top things you need to know about IR. Okay. And if there's no questions, acid-base reactions. Remember, we have to know two kinds of acids and bases in organic chemistry. The first kind are what we call Lewis acids. Lewis acids want to accept electrons to make a new sigma bond. Lewis base has electrons to share to make a new sigma bond. So if you can think about it, a Lewis acid is something that does not have an octet or possibly has a charge. A Lewis base is something that has an octet and usually a lone pair. And that lone pair is what's used to come out and create the new sigma bond. Lewis bases also can have charge because they're going to have a full octet, and that might not balance out their atom that they're around. So you're looking for that in your Lewis acids and your Lewis base. The other type of acid base we need to look at is our Bronsted Lowry. And our Bronsted Lowry tells us that we have an acid. When it reacts with a base, it turns the acid into the conjugate base. It turns the base into the conjugate acid, okay? And knowing which way the equilibrium lies, you compare the acid strength of the original acid to the acid strength of the conjugate acid. That's all you have to compare, is those two things. Whichever one is the weaker acid, the higher pKa value, you know the equilibrium is going to lie in that direction. Okay, so you're always looking for comparing the two acid strengths, and whichever has the higher pKa value, which is the weaker acid, makes it shift in that direction. Okay. Here are blocked out a few of the ones you kind of need to know where they are, at least relatively. You need to know that alkynes are more acidic than alkenes that are more acidic than alkanes. Alcohol and water are about the same. Where acetic acid is, and knowing what higher, what the very acidic compounds like hydronium ion and HBr are. How do you determine the pKa values? The pKa values are actually measured. And so you can't actually calculate them empirically. Well, you probably can now with quantum mechanics, but these are actually measured. And so they're measured and tabulated for your, but knowing where these few values are, you should be able to accomplish most of the work we're going to be doing. Okay. All right. So, but acid strength can change. And some things that affect acid strength are these four things that we're looking at: electronegativity and size. Okay. Electronegativity first, size. So if they have the same electronegativity, but one's bigger, the bigger atom is going to be more acidic because it spreads that charge. The second thing is resonance or delocalization. Again, spreading out the negative charge on your anion makes it a more acidic compound. And don't forget the inductive effects. The inductive effects are actually pulling electron density through sigma bonds. And so if you're pulling electron density away from a sigma bond, it becomes more acidic. If you're donating electron density, it's going to be a less stable anion, it's less acidic. Does electronegativity have the highest priority when coming to acids? Actually, size is the higher priority. If you have two things of similar electronegativity, size is always the factor. If they're close together, for example, in the series, iodine is more acidic, iodic acid is more acidic than hydrobromic acid, which is more acidic than hydrochloric acid. So in resonance, most of the time when we have resonance things, they are less acidic than the real acids, but you can see it on the chart because the acetate ion uses resonance to make it more acidic. So if you can draw a resonance structure, then it will be more acidic than if you can't draw a resonance structure. Okay, that's the key there. Okay, and then don't forget hybridization. Hybridization is SP is more acidic than SP2, which is more acidic than an SP3. Okay. All right, questions on acids and bases real quick? Okay, so I mean, these are just the topics you need to make sure you understand, and kind of they should mirror what you see in the homework examples as well. All right. So in module 4, we learned about conformations of straight chains and cyclic alkanes. And we learned that we have different positions available to us. We have what we would, and we know that as we rotate around, we can go from a staggered conformation to an eclipsed conformation. And going from a staggered to eclipsed conformation takes more energy. Okay, because the electron clouds are starting to butt up against each other, and it's starting to push out, giving us torsional strain. Okay. Now, once you start adding larger groups to it, we now have different conformations available to us. We have what we call the anti-position right here, where the two big groups are opposite each other. Then we have our first staggered position. Then we have it where our two groups are near each other, but not. I'm sorry, this is the first eclipsed position, where the two groups are close to each other, but they're not eclipsed. And we call that gauche. That's a gauche interaction. And that's spelled this way right here, okay? And then we can go to our eclipsed, which has the highest energy available to us, go back to a gauche, go to a eclipse, but again, the larger groups are not eclipsed with each other. And then we get back to our anti. Our anti is always going to be the lowest conformation. Our eclipsed with our largest groups is always going to be the highest energy conformation. Okay. But notice this gauche never gets back to 0. Okay. Only the anti gives us that lowest energy potential. And we can apply that rule to cyclohexanes as well. Okay, we applied that rule to cyclohexanes to see which is going to be, whether a group is going to be in the axial position or the equatorial position. Okay, and these are some of the conformations available to us in cyclohexane. Again, chair is the most stable here because all of these bonds are as far apart as possible and give you that 109 degrees, 109.5 degrees. Any deviation from that, the more, like for example, this has 5 atoms all in a plane. That means every single thing that's attached to those carbons is now eclipsed, right? So now you have 1, 2, 3, 4, 5 sets of things that are eclipsed. That's why it's highest energy. Okay. In the boat, you only have these 2 that are eclipsed and these 2 are eclipsed. That's why it's not as high in energy as the half boat. And then these have fewer eclipsed. And then eventually we'll get back to a chair position. And again, room temperature is enough heat to have it flipping back and forth from all these so that you can go all the way from this chair to this chair and it'll keep flipping back and forth until it has a substituent on it that makes it have a preferred position. And our preferred positions have everything to do with looking at that Newman projection about whether they're gauche or staggered. And again, whether they're gauche interactions or whether they're anti-interactions. So if you can have your big groups be in a anti-configuration where they would be opposite each other or in a gauche position if they're next to each other, they will be trying to be those equatorial positions. Big groups want equatorial positions. And in the boat one thing is the positions, you gotta remember the positions are axial and equatorial for the chair position. But once we get to the boat position, we have a new one. It's called the flagpole, okay? And when we look at our Newman projection of our boat position here, you see the reason it's such a high energy section is that we have all of our elements are eclipsed, including these 2 carbons in the middle, are all eclipsed. And that's what's giving us our high energy system. Okay, and the last thing that you need to remember about these cyclohexanes is that the bigger the group, the more time it's going to be equatorial. And no matter anything larger than hydrogen is going to make it position itself so it's the equilibrium lies more toward the big group being in equatorial position. And as you get to something really big, like this tubular group there, it's going to be there 99.9% of the time. And that is my last review slide, and we're right here at 10:50. I'm going to go ahead and stop recording. Stay by if you want to ask questions, but I want to get the recording done at the right amount of time. Stop sharing.